Hey guys, we're taking a look at derivative of exponential functions. We're going to find out why the derivative functions look the way that they look, and we're going to end up using a bunch of the different derivative rules that we've already been discussing. So in case you forget, a little bit of review of exponential functions. They look like, as you see over here on the right, some of them grow and some of them decay. The traditional one, the parent function that we often look at is this y equals 2 to the x power. We start out growing slowly, and then it grows more rapidly as x increases. If the base is a larger number, like 5 to the x instead, then it grows more rapidly, as you see here. Or if it's closer to 1, a little bit less than 2, you'll see that it grows less rapidly. If the b value were exactly 1, then you would just have a line. You can also have some exponential decay functions, 0.2 to the x or 0.5 to the x, and you see how they change as well. So a couple other things. For all of these, as long as you know horizontal or vertical translations, you'll always be passing through the point 0, 1. It is asymptotic to the x-axis on one end, whether that's the negative x or the positive x, and all of the values will be positive for those distributions there. Okay? So we're going to go through this quick investigation to find the derivative and then apply it to different settings. So what we're looking at here is we're focusing on the exponential growth function y equals 2 to the x. Now, starting with these x values, you can find the y values just by plugging them in. I'll save you some time there. That's just 1, rad 2, 2, 2 rad 2, and 4. All right. Now, if you wanted to find the dy dx, well, we don't know the derivative function yet, but if you wanted to find the derivative at these different x values, you could just go to the calculator, plug in y equals 2 to the x in y sub 1, and then go second calc, select option 6 for dy dx, and then just enter in the x value to find the dy dx that you're looking for. Again, just saving you some time. These dy dx are these derivative values that these x values are 0.693, 980, 1.386, 1.961, and 2.773. And then in this column here, it says take your derivative function and divide it by the y. Well, again, just doing some simple arithmetic, I get 0.693 for the first one, and it just so happens that I get 0.693 for all of them. Now, what that tells you is that there's clearly a relationship between what the dy dx value is at x equals 0 and what the derivative function is going to be. What that relationship is exactly is something that we'll spend more time with at the end of this lesson, okay? But instead, we're going to spend more time focusing on a specific exponential growth function that we'll see in just a moment. Now, if you wanted to see this relationship again, you could just go ahead and repeat it for different b values, all right? But the idea, the goal of what you wanted to see is that the derivative for an exponential growth function, if f of x equals some b to the x, then f prime of x, the derivative function, is some constant k times that original function b to the x, where k is the constant equal to f prime of 0. Now, from that, if you wanted to actually find the derivative, you would need to know what f of prime of 0 is. Now, if f prime of 0 equals 1, then you have a function that's its own derivative. And that exists when b equals 2.718, and hopefully that value, 2.718, looks familiar. In fact, it's e, that magic number e that we talked about. All right? Now, what does that mean? That means if you have f of x equals e to the x, then f prime of x also is e to the x. And obviously that's important because if you know that the derivative of e to the x is e to the x, then you can find other derivatives that include e to the x within them. And that's what we're going to take a look at right here. Now, just quickly about e to the x, just like we reviewed exponential growth functions, we could see what that function looks like. We know that as x approaches infinity, y approaches infinity, that means dy dx also approaches infinity. Also, as x approaches negative infinity, y approaches 0 because we have our asymptotic relationship. That tells you that dy dx also approaches 0. Because if I try to find the derivative, the slope of the tangent line at any one of these values, that slope is pretty close to 0. And if you were to go out further to the left on the x-axis, we would see that relationship even more so. Now, like I said before, the derivative of e to the x is e to the x. But what if we had e to something other than x? How could we find that derivative? Let's just say we had e to the negative x, or e to the 2x plus 3, or e to the negative x squared. Well, we can find these derivatives pretty quickly as long as we remember how to use the chain rule. If we have e to the f of x, we could think of the e to the u, where u equals f of x. So, for instance, if we were looking at this problem here, we would have y equals e to the u, where u equals negative x squared. And that helps us because if we're trying to then find a derivative, the derivative of dy dx, we can just do dy du times du dx. dy du is just going to be u times e to the u minus 1, and du dx is just going to be negative 2x. And then we can go ahead and plug in those and plug back in what u is, etc., like that. And we'll see examples, obviously, in just a moment here. So what do you need to make sure you know? The derivative of e to the x is e to the x, and by the chain rule, the derivative of e to the f of x is e to the f of x times f prime of x. Again, just an application of the chain rule. All right. So let's look at some examples here. We see first we have 2e to the x plus e to the negative 3x. Well, first of all, we have the addition rule. Because these two are being added together, we could treat the first part just as we would any other function. And we already know the derivative of e to the x is e to the x. So we can start out by saying dy dx equals 2e to the x, because the derivative of e to the x is e to the x, and the 2 just comes along for the right because it's a constant there. Then, to talk about the second part, this e to the negative 3x, we're just going to take e to the x, or e to the f of x, excuse me, times the derivative of the exponent. So this part right here is the dy dx of negative 3x. That's how we have the negative 3 there. And then we look to see if we can do any simplifying. Really can't do any simplifying other than just moving that 3 in front. The next one we see, we have x squared times e to the negative x times, telling me that we're going to be doing some product rule work there. As you see, product rule. So we're just going to say, all right, u equals x squared, so u prime equals 2x, v equals e to the negative x, so v prime, using what we just talked about the derivatives here, is just going to be e to the negative x times the derivative of the exponent, which is just negative 1. So all I have to do now is just go ahead and apply the product rule to find this derivative. So if we look at this here, the product rule says u prime times v plus u times v prime. So this is just going ahead and plugging in u prime is 2x, v is e to the negative x, u is x squared, and v prime, as we just showed down here, is e to the negative x times negative 1. Then just doing the quick step of taking this -1, moving it in front. Now we just have that minus there, and that's all that we can do. There's no more simplifying to do in this problem. So let's see. In the first one, we just used our addition rule. In B, we use the product rule, and here in C, we see we have a quotient, so we're going to be using quotient rule. All right. So if we go ahead, let's see. We can say that U equals e to the 2x. So U prime is going to be e to the 2x times the derivative of the exponent, which is just 2. We have v is x, and therefore v prime is equal to 1. So using the quotient rule, which says u prime times v minus u times v prime all over v squared, we're just plugging in. So right here we have u prime times v minus u times v prime all over v squared. Now if you look at it here, in the numerator, I have e to the 2x, e to the 2x. I can pull that out and then put in the 2x minus 1 over x squared. Some might argue that's not necessarily more simplified. Others might argue it would be. Anyway, this is the best answer that we could have for this particular problem. All right. Let's take a look at these two. Again, just more applications of different rules to go ahead and find these here. So you might want to pause this video and try these two on your own, or you can just follow along with me. It's up to you. So as I look at A here, all I'm going to be doing, let's see, I have a binomial raised to the third power. Looks like the chain rule. So I'm just going to go ahead and take the dy du and multiply that by du dx. So I have u cubed, the derivative there is 3u squared, times du dx. All right, well, when I look at du dx, I'm really talking about the derivative of e to the x minus 1, and the derivative of e to the x minus 1 is just e to the x, right there. So just move that guy in front. 3 e to the x times e to the x minus 1 quantity squared. Same deal here in B, except now I have this radical in the denominator. So go ahead and start by rewriting 2e to the negative x plus 1 now raised to the negative 1/2. And now I can go ahead and say, all right, I really have y equals u to the negative 1/2, where u is this function here, 2e to the negative x plus 1. Chain rule application, dy du times du dx. So dy du is negative 1/2 u to the negative 3/2 times du dx, where I'm just going to take the derivative of this guy here, and the derivative of 2e to the negative x plus 1. Well, the 1 just goes away. We don't need to deal with that. But the derivative there is going to become 2e to the negative x times the derivative of the exponent, which is just negative 1. Also, you need to make sure to plug back in what u equals. And now, since this is all multiplication, just go ahead and multiply it out. I have the negative 1/2 times the 2. They cancel out, other than the fact that it's going to be a negative. But I also have this negative out here, which is going to make the whole thing positive anyway. So I really just have my e to the negative x from here times what I have in the parentheses there. And while the answer here shows it left as a negative exponent, I would refer you to this last part here, where we go ahead and put it back with a positive exponent and say that it is equal to the e to the x over e to the negative x, over the square root of 2e to the negative x plus 1 raised to the third power. This is a slightly better answer to that problem there. All right, so that's it. That's how you find the derivative for e to the f of x function. Now, what we haven't really talked about is, well, what happens if it's not e to the x? We talked about it in the investigation at the beginning, but now we need to talk about how to deal with it in other parts of the problem. Okay? The good news is for us that if we're looking for the derivative of some a to the x where a is positive, it's just going to be a to the x times the natural log of a. Again, all we're really doing is applying the chain rule once more to get this dy dx equals a to the x times the natural log of a. Right? Now, the good news is that this rule, like all the other rules, are provided for you in your formula packet that you get on the IB exam, so you don't have to worry so much about memorizing. You just need to know how to apply it. All right? So that kind of wraps up what we're talking about here. Again, what were we trying to do? We were trying to find the derivative for a variety of exponential functions using a combination of different derivative rules. I think we met that objective. Obviously, you could do some more practice and see how you feel with it. That's it for today. Have a good day.